Dear students, in the previous lecture, we had started discussing the content-based web mining techniques, and therein we had already discussed that a couple of text pre-processing steps are required, namely stop word removal and stemming. So after having done those two text pre-processing steps, the first and the foremost technique that we can discuss in the content-based web mining is the term frequency technique, right? So the frequency of a word in a given document is a good measure of its importance. That is the first beginning. More frequent a word is in a document, more important that word is in that document. But of course, this will hold only when we have done away with the stop words. That is, we have done the stop word removal. Otherwise, what will happen? Articles like of, a, and, the, for, which are otherwise stop words, if we don't remove them, they will come at top whenever we are counting the frequency of the words in a document. Likewise, stemming should also have been done before the frequency of a word could be taken into account. So this may be the good first step. The frequency of a word in a given document is a good measure of its importance, valid only after text pre-processing, both of them that we discussed already. Now, can we improve upon it? Yes, we improve upon it by not just taking term frequency, but also the inverse document frequency into account. Let us understand what do we mean by inverse document frequency. By this, what we want to have is that a word should be frequent in the current document, but not so frequent in the rest of the documents. So that way, the uniqueness of a word to a document and hence its relevance is gauged, is measured, right? Probably stems from the fact of the information theory that information is inversely proportional to probability. An item would become a breaking news only if it is less probable. Something which is more probable doesn't form a good news. For example, if somebody says that India defeated Bangladesh, may not be that big a news because that was very probable. But if it is the other way around, Bangladesh defeats India in cricket, that becomes a breaking news because that was unexpected, that was least probable, right? Likewise, if somebody says that some sun rises in the east, no news. You will never see in a newspaper that sun rose in the east today because that is almost certainty. But if someday it happens that sun rises in the west, that will be the headlines of all the newspapers because nobody was expecting that sun will ever rise in the west. So lesser the probability, more the information content and vice versa. So likewise, a word has to be frequent in the current document, but not so frequent in the rest of the documents. If it is frequent in all the remaining documents also, then there is no uniqueness of the word in the document. So what do we do? This is your FW by FW max, where FW is the frequency of the word in that document and FW max is the frequency of the maximum frequency of any word in that document. So this is basically the normalization factor so that this ratio remains between 0 and 1. Now log row by row W, this is your IDF. This is IDF. So this is TF and this is IDF and we multiply both of them. By row, I mean the total number of documents in the corpus. And row W are the number of documents that contain the word W. So if row and row W are same, that is the word W occurs in all the documents. If row is equal to row W, then this will become 1 and log 1 is 0. So 0 multiplied by, even if this is 1, that will be 0. So what we want ideally is that the word should be very frequent in this particular document, but not so frequent in the rest of the documents. Right? So what is the concept of TF-IDF? We'll elaborate more upon it after we have seen the next technique, vector space model. We will take some examples, and over there we will see how term frequency, inverse document frequency combines with vector space model, and then the idea will be more clear, right? I hope it is reasonably clear by now, but it will be more clear when we take up the example. So just this description of the symbols. FW is the frequency of the keyword W in the document. FW max is the maximum frequency of any word in the document. Row W is the number of documents in which this keyword occurs, and row W, sorry, it should be just row. Row is the total number of documents in the collection. So this is wrong. Row is the total number of documents in the collection. An alternative formulation is given as, people have come up with alternative formulation. So this may be the alternate formula, but the simpler one remains this one. FW by FW max log row by row W, right? Now let us take the next technique before we try to combine both and try to take the examples pertaining to them. The other technique for content-based web mining is the vector space model, in which we assume an n-dimensional vector space with one dimension for each term. So each document or query is represented as a term vector in this vector space. Each component of the term vector is either 0 or 1, depending on whether the term corresponding to that axis is absent from or present in the text, right? The similarity between a document and a query is the dot product of their term vectors. We can also calculate the angles between the term vectors of the query and the document. Let me take an example. Suppose I'm talking about a language which has just 3 words in it. In order to make it simple, in order to make it explainable, because 3 dimension is the maximum that we can visualize on a piece of paper. So suppose I have W1, W2, W3, 3 dimensions. Now, if there is a document which contains W1 and W3, so that will be represented by the term vector, this term vector having components 1 and 1 in the directions of W1, W3. So this may be a document D1. Now suppose there is a query which contains W2. So it will be represented here, query. If you try to find out their dot product now, so this will be a term vector, so that is why this symbol, vector symbol, and query is also a symbol. So you try to find out the dot product. Now this is in this plane, and Q is orthogonal to it, perpendicular to it. So when we take the dot product, it will be the cosine of the angle between them. Dot product says mod D1 mod Q, cosine of the angle between them. Angle between them is 90 degrees and cosine 90 is 0. So no similarity. It makes sense because document at hand contains W1 and W3, whereas the query is looking for, there's no overlap. So their similarity is rightly assigned as 0, right? There could be a case wherein suppose Q contains not just W2, but it also contains W3. Okay, so there will be a term vector corresponding to this, like this, right? Which contains Q may be W2 and W3 cap, W2 cap plus W3 cap. So the cosine of the angle between them, that will become more important. So the similar, likewise, we can go on adding the dimensions, and there will be as many dimensions as are the words in that collection or in that language, right? So this is how vector space model works, right? So this is to begin with. Alternately, each component of the term vector is taken as a function that increases with the frequency of the term corresponding to that axis within the document and decreases with the number of documents in the collection that contain this term. So one way could be to combine vector space model with just TF, term frequency. In that case, what will happen? I won't take a unit vector, rather I'll take the magnitude of the vector as many times W1 occurs in the document D1. So it may not be just one, it may be like 3, 1, 2, 3, right? So our term vector in that case will look something like this. 1 occurrence of W3 and 3 occurrence of W1. So that will just be in which, again going back here, and decreases with the number of documents in the collection that contain this term to take into account the TF-IDF factor. The term vectors of documents must be normalized to 1 so as to compensate for different document lengths. Once again, FW should be divided by FW max so as to take into account the length of the document. Because one document may be very lengthy or the other may not be that lengthy. So in that case, the frequency of the word in one document may be lower and in the other document may be higher. And that is happening not because of its relevance, but because of its length. So that is why we divided by FW max, so that it remains normalized and the length of the document doesn't have an effect on our result. Now let us take some interesting examples. Suppose for two small resources, the frequency of words occurring in them is given below. So we have two resources, two documents, R1 and R2. Suppose W1 occurs twice in R1 and 4 times in R2. W2 occurs 0 times. That means it doesn't occur in R1 at all, but it does occur in R2 3 times. W3 occurs 4 times in R1 and once in R2. W4 occurs twice in R1 as well as twice in R2. And W5 occurs 3 times in R1 and 0 times in R2. Find out the similarity between the sources R1 and R2 using the vector space model. How can we do that? How can we do that? We are just doing the term frequency thing. We are not taking into account the IDF as yet, right? So in this example, let us first take just the TF combined with vector space model. So in fact, this should be R1 dot R2. This should be R1 vector dot R2 vector. So how can we find out? 2, 4 are 8, plus 0, 4 ones are 4, plus 2 twos are 4, plus 3 zeros are 0, which is 16. So this becomes the R1 R2. Now we all know that R1 dot R2 is equal to mod R1 mod R2 cosine of the angle between them. So what value will the cosine of the angle between them would have? It will be R1 and R2 divided by their magnitudes. And what are their magnitudes? 2 square plus 0 square plus 4 square plus 2 square plus 3 square under root. So 4 plus 16 plus 4 plus 9. And this will be 16 plus 9 plus 1, 16 plus 9 plus 1 plus 4 plus 0 under root, right? So it will be 16 R1 dot R2 divided by mod R1 mod R2, right? So 16 upon root 33, this will be root 33 and this will be root 30. If you calculate it, it will be 0.5085. So 0.5085 will be the similarity between the resources R1 and so the similarity between the two resources R1 and R2 using the vector space model and term frequency will come out to be 0.508. In the next example, we are going to see how can we have vector space model combined with TF-IDF. So this will give you an idea how TF-IDF has to be worked and how we can combine them, right? So that will give us an idea. So let us take the next example, wherein frequency of words in resources are given. Suppose words, but W1 occurs 0 times in R1, twice in R2, and 4 times in R3, and likewise W2 3 times in R1, 0 times R2, and once in R3, and so on. So over here you see that I've listed the words, I've listed their frequencies, right? 03580, so 03580 like this, and 20061, so 20061, and 41031. Now see the maximum frequency FW max in all these documents is 8 for R1, 6 for R2, maximum of all these values, and 4 for R3, right? So when you are trying to find out the relevance of W1 in R1, since this is 0, so 0 upon anything into anything will be 0. So that is why I have kept it as 0. Come to W2. It is 3 by 8. FW by FW max. 3 by 8. Right? Log total number of documents are 3, and there are 2 of them in which this occurs. It doesn't occur in R2. So 2 of them. So log 3 by 2. Right? Likewise over here, it is 5 divided by 8 because 8 is FW max. Log 3 by 1 because it doesn't occur in 2 of them. It occurs in only one. So it is log 3 by 1. It will be 8 by 8, but log 3 by 3 because it occurs in all of them. So over here you see, even though this is the most frequent word in this document, and this in fact was FW max, so 8 by 8 would be 1, but log 3 by 3 will reduce it to 0 only. So even though this word is frequent here, but this is frequent in all the documents, and that is why its value will be 0. So what and this 0 will give you 0 anyway, because 0 multiplied by anything will be 0. So now I can write the term vector corresponding to R1, which I have done here. R1 vector is equal to 0 times W1 cap plus 3 by 8 log 3 by 2. I've calculated here. You see, somewhere I must have done it. You do it. You can see that this will be 0.066 W2 cap. Then you calculate this value. It will be 0.3 W3 cap plus 0 times W4 cap. Just hold on. 0 times. Why 0 times? Because log 3 by 3 would be 0, and 0 multiplied by this will be 0. So 0 times W4 cap and 0 times W5 cap. Okay. So this will be the term vector corresponding to resource R1 in different dimensions of the words. If we come to R2, FW max for this case is 6. So it will be 2 by 6 frequency of the word in this document divided by the maximum frequency of any word in that document. So it will be 2 by 6. The maximum frequency was 6. So 2 by 6 log 3. Total number of documents remain 3. And the number of words in a number of documents in which this word occurs is 2. It is 0 here. So it occurs in just these 2. So log 3 by 2. These 2 will be 0 anyway because the frequency of the word in that document is 0. So 0 divided by anything or multiplied by anything will be 0. If you come here, it is 6 by 6 log 3 by 3 again. So this will again be 0. Even though it is having the maximum frequency, but this log 3 by 3 will reduce it to 0. And in this case, it will be 1 by 6 log 3 by 2 because over here it is 0. So total number of documents are 3 and only 2 of them contain this word W5. So I can write down the term vector corresponding to R2, right? So R2 will be this 2 by 6 log 3 by 2 will be 0.06 W1 cap. It is in the W1 cap plus 0 times W2 cap plus 0 times W cap plus 0 times W4 cap because log 3 by 3 is reducing it to 0 and 0.03 times W5 cap. Likewise, I can do it for R3. The maximum frequency is 4 only. So 4 by 4 log 3 by 2. So over here, it will have a non-zero value. It is having the maximum frequency. So 4 by 4 log 3 by 2 because it doesn't occur here. Right? So log 3 by 2. 1 by 4 log 3 by 2 again because it doesn't occur here. 0 because the term frequency itself is 0. 3 by 4 log 3 by 3 will be 0 again. And 1 by 4 log 3 by 2. Right? So the term vector corresponding to R3 will be 0.176. If you calculate this, this will be 0.176 W1 cap. Plus, if you calculate this, it will be 0.044 W2 cap. Plus 0 times W3 cap. Plus 0 times W4 cap. Again, this is 0 because log 3 by 3 will be log 1, which is 0. And finally, 0.044 W5 cap. The calculation of this will be 0.044. So I've got 3 resources. I can find out this. One of these resources may be Q, right? The query or the document, anyone may be taken as a resource. So suppose I have to find out the similarity between R1 and R3, where R1 is the query itself. So in that case, it will be R1.R3 will be 0 times 0.176 will be 0. 0.066, 0.044 will be 0.003. Then this will be 0 again, multiplied by 0 here, right? And this will also be 0. 0 multiplied by 0, and then 0 again multiplied by 0.044 will be 0. Okay, so a 0 here too. So R1 dot R3 will be this. Cosine of the angle would be 0.003, which is the value of the dot product divided by their magnitudes. So R1, R3, their magnitudes are 0.066 square plus 0.3 square. These are the only non-zero values. The rest of them are all zeros. There's no point in making plus 0 square plus 0 square plus 0 square, right? And over here, it will be 0.176 square plus 0.044 square plus 0.044 square again. You take the under root, so it will be 0.003 divided by 0.307 into 0.187, which is 0.052. So this will be the similarity between R1 and R3. As I said, suppose your query similarity between R1 and R2. We have found out for between R1 and R3. You find out between R1 and R2 and see whether the query which is represented by R1 is more relevant to R2 or more relevant to R3. The relevance of the query to R3 I've already found out 0.052. You do it for R1 and R2 to see the similarity between the query and R2. Right? So whichever is more relevant will come on top, and whichever is less relevant will come below it. Right? So let me take one last example to make things more clear. This in fact is a combination of the previous 2 examples. Suppose I'm given the data like this. There are 6 words for the change, 3 documents. Their frequencies are listed here. 021 and 865, 500, 318, 022 and 437. So without IDF, I can just write their term vector with just TF and not IDF. How can I write it? R1 will be 0 times W1 cap plus 8 times W2 cap plus 5 times W3 cap plus 3 times W4 cap plus 0 times W5 cap and W6. Likewise, R2 will be 2 times W1 cap. You see here, 6 times W2 cap, 0 times W3 cap, 1 times W4 cap, 2 times W5 cap, and 3 times W6 cap. For R3, it will be 1 times W1 cap, 5 times W2 cap, 0 times W3 cap, and then 8 times W4 cap, 8 times W4 cap, 2 times W5 cap, and 7 times W6 cap. So this will be the term vector with just TF, taking TF into account, right? In case you want to have just the term vector without even taking TF into account, in that case, all the zero values will remain zero and all the non-zero values will become one. If you don't want to have TF even, right? For example, R1 will be 0 times W1 cap plus W2 plus W3 plus W6 cap, right? Now suppose I'm taking to the highest point wherein I'm taking into account both TF as well as IDF. The above is without IDF, just having TF. If without IDF you want to calculate the similarity between any of these two, you can go ahead and do it. Find out their dot product and divide that dot product by the magnitude of the individual vector. So that will be the cosine of the angle between them. Higher the cosine of the angle between them, more similar they are. Ideally, if suppose they are completely overlapping, suppose this is one document or the query and the other document and the query is completely overlapping. So cosine of the angle between them is 0. And cosine 0 is, the angle between them is 0. So cosine of the angle between them will be 1. Most similar. Right? So if they are perpendicular, that means no word in common. So their similarity will be 0. If they are completely overlapping, that means all the words are in common. So their similarity will be 1. Right? So if we go to the other extreme to find out the similarity between them using TF as well as IDF. So if you want to keep vector space model along with TF IDF, then in that case, I'll have, suppose I want to find out the similarity between R2 and R3. So I'm not giving the column corresponding to R1 here because I just want to have R2 and R3, but that doesn't mean that R1 is useless because finding out log row by row W, it will help, right? So for R, this is 2 by, what is the maximum frequency? It is 6, right? So 2 by 6 log 3 by 2 because it doesn't appear here. 2 by 6 log 3 by 2. This will be 6 by 6 log 3 by 3, which will be 0. Okay, this will reduce to 0 only. This will remain 0 because the very frequency is 0. So FW itself is 0. So dividing it by FW max 0 by 6 log whatever will remain 0. This will be 1 by 6, 1 by the maximum frequency log 3 by 3, which will again be 0. Right? 2 by 6 log 3 by 2 and 3 by 6 log 3 by 3 again, which will again be 0. Okay, so I can write R2 as 2 by 6 log 3 by 2 will be 0.06 W1 cap plus 0 plus 0 plus 0, 0 times W2 cap, right? 0 times W2 cap, 0 times W3 cap, 0 times W4 cap plus, now this will be non-zero, so 2 by 6 log 3 by 2 will be calculated as 0.06 W5 cap, and then again this is 0. Coming to R3, 1 by 8 log 3 by 2. 1 by the maximum frequency is 8 log 3 by 2 because this is occurring in 3 of them, right? Okay, so accordingly you can calculate 1 by 8 log 3 by 2 and then 5 by 8 because maximum frequency is 5. So log 3 by 3, this will again be 0. This will be 0. Now this also remains 0 because the very frequency itself is 0. And this is 0 because log 3 by 3 is 0. It is occurring in all 3 despite the fact that it is having the maximum frequency. 2 by 8 log 3 by 2 will be a non-zero component. 7 by 8 log 3 by 3 will again be 0 because this is this word is occurring in all 3 resources, right? So the term vector corresponding to this will be 0.022 W1 cap, which will be the calculation of 2 by 6 log 3 by 2 plus 0 plus 0 plus 0, which means W2 cap, W3 cap, W4 cap. And then W5 cap will be 2 by 6 log 3 by 2, which comes out to be 0.044 W5 cap, and then again a 0 here. So cosine of the angle between them will be the similarity between the resources R2 and R3. One of them may be query, both of them may be resources, right? Whatever way. So this is 0.06 into 0.022 plus 0.06 into 0.044, right? Rest of them are all zeros, so we are just leaving them out, divided by the magnitude, which is 0.06 square plus 0.06 square. And this will be 0.022 square plus 0.044 square. So if you calculate this in the numerator, you will get 0.00396, and in the denominator, you will have finally, it comes out to be 0.947, which is very close to 1, which is very close to 1. So there's a very good similarity between R2 and R3. If my calculations are correct, hopefully they are correct. Okay, if they are incorrect, you can always point out. So two techniques have been exhibited by the three examples that I have given here. In fact, we can have three techniques: term frequency alone, then term frequency combined with IDF. There is no point in having IDF alone. IDF will come always with TF only. Right? So TF, IDF, and then we have vector space model, and then you try to combine vector space model with TF only, or vector space model with TF plus IDF. So that way, so many combinations of the content-based web searching may be done. Okay, so we will stop for today, and we can continue from here on in our next lecture. Thank you very much.